Characterization and Applied Thermodynamics. He is invited guest of the EFCE Working Party for Thermodynamic and Transport Properties, the advisory board member of Journal of Chemical Thermodynamics and Thermal Analysis, and he is member of the Royal Dutch Chemical Society. We are very happy to have you here today, and we are very curious for your talk, Electrolytes in Industries versus their salt. Antoon, the floor is yours.
Thank you very much, Gabi, for your very kind introduction. And thanks very much to the organization for inviting me, and thank you, audience, for having me here. I would try to have my avatar facing you while I'm looking also at the screens. It should work. Let me see.
It works.
Okay, I'm happy to see that. Now I have to move this. This is a very strange world as we're living in today. So I was hoping that we would have this meeting together last year, actually, and that we would have had it in Paris. And that's not the case. So now we have this in this virtual space, which is also exciting because you can do things that I normally cannot do. So if this works, you can see me jump around. I hope you did. I can't see it myself. Electrolytes industry, worth their salt. That is the title of my lecture. And what I'm hoping to be able to get across is the importance of electrolytes. I think we all of that are aware of that. But also that in industry, even though maybe not everything is unraveled yet, we still need to find ways to get our models into place. So my lecture will comprise three major elements. One is setting the scene. Then I will provide a few examples from Nouryon, and then I will end with a perspective. So, electrolytes are everywhere in our lives. Obviously, we know them as salts, ranging from table salt to road salt to remove snow. Well, this is not really the time of year to consider that, but it's also relevant. From batteries, which are, of course, very relevant in the energy transition that we're in the midst of. Electrical cars that are coming up, but also in the chemical industry, and not only the chemical industry of today, but also the chemical industry of tomorrow, when biotech is, can be assumed to have a very important role there. Think about biotech processes. Many fermentation processes actually produce salts in diluted form. And then the active ingredients need to be extracted from that. There's a lot of electrolytes in there. A very classical electrolyte situation is corrosion. And so there are many things that we should consider. Next slide. How's this not happening? Sorry about that.
No, it worked.
Why is this?
Challenges in electrolytes.
Okay, so there's one slide missing, I'm afraid. And it worked in the test. There it is. So the challenges in electrolytes are many. And it starts, of course, with the fact that electrolytes have a very complex nature. Certainly, if you compare it to the ordinary molecules that we know of. If you look at electrolytes, the availability of data is also a concern. I will get back to it, but it certainly provides a challenge if we want to understand the nature of electrolytes. Another aspect is that the modeling framework that we want to use, one can wonder how good do we really understand all the effects that needs to be modeled. And certain effects are maybe counter-effective. So if you describe one, it's counterbalanced by another, and actually you're looking at the residual. So small errors in one can create a big effect in the total effect. And as an advanced user, we also see the challenges that we have in parameterization. So even if frameworks are offered through software, we have difficulties in getting the right parameters in there. So what is there a preferred order of parameterization? And if so, what is that order? On top of that, a number of parameters have a strong correlation, which makes, of course, the determination more difficult. So if we want to get to the next level of electrolytes, we could think of a tree of wisdom that starts with data. Data is the beginning of many things, or maybe you should say observations are the beginning of the development of science. If you have a lot of data, you can retrieve information of it, and that information then can be transformed in knowledge. And if you have a lot of knowledge, then you can reach the final state of wisdom. If you look at this figure, then you can say that the data, if you have a model, are crucial for parameterization. If you don't have sufficient data or of insufficient quality, then you will have difficulties in parameterization. The data also, as I just said, provides you through information and knowledge to the wisdom that you need to develop a model framework. But it can also say that you need a lot of knowledge once you want to make use of a model framework, how to select the most preferred framework, and next, how to parameterize that. So we need all parts of the tree of wisdom. If you then look at the situation for data, this is an attempt for me to show you the forest of data as an example of all sorts of data that we have. If it comes to electrolytes, there are many different forms of salts, different cations, different anions, different solvents. Water, of course, is very well known, but also other solvents, mixed solvent electrolyte systems. And on top of that, you also have the range of conditions that we're talking about. And if you look at the data, there's a lot of data for aqueous solutions and the typical salts, chlorides, iodides, sodium, potassium, that sort of electrolytes. But there's less of the others. So we're dealing with a description or data availability in the forest, which is of varying availability. I first put limited, but it's actually varying depending on the system that you're looking at, of varying spread, meaning there's a lot of data, for instance, at ambient conditions, but there's hardly, far less data available at, for instance, 200 C, if that is of relevance to you. And also the quality of the data is varying. So we can ask the question, why do we want to have the models? And this is a very schematic representation of a lifetime of a process or a new product, where you start with development. Let me see if I can put on the laser. So you start with the development phase and the construction. So here you only make cost, no earnings. then the production and the sales start off, so you're gaining money until the end of the lifetime, and then you have to do something for the end of life situation. And of course, you have key factors like time to market or time to profit, which are very essential. But what we really want to achieve is, of course, can we improve the earnings? And we can do that by minimizing the investment or reducing, well, in the end, to reduce the time that we get to the profit, or that we maximize the profit in various ways, and that we can prolong the life cycle of this product or process. We can all do that, and making use of, if you have a fundamental understanding and the models available, and can apply our chemical engineering capabilities. So what we're after actually is to have a toolbox of that kind of capabilities that can help us to do all these things. And a good thermodynamic model and good data is one of them. So if we look at the purpose of the model, we want to simulate plant practice. And you can do that by, as shown, hitting your computer screen. But actually, of course, what we want to do is to simulate the process in reality and to find more optimal ways to operate it. And that can be optimization. It can also be a complete debottlenecking or even a complete new plant. So if we look at the model, its purpose is actually that we have a fair representation of the system of concern, and we want to have that to support engineering decisions. So even if the model is wrong, it doesn't matter so much. So to speak with George Box, essentially all models are wrong, but some of them are useful. And especially that aspect is what we're after. And that's pretty much in line with also what Clausius said, our friend. I understood he is also from IFPN, or École des Mines. And he phrased that nothing is as practical as a good theory. And I have to say, I have to agree with him. So the model is not the goal itself. It is a supporting means to get somewhere. It must be representative, but also means that we can live with a little bit of inaccuracy or inadequacy. Well, in the same way, you could look at the data, and the data, they are really important because that is the start of everything. With the data, we have been able to develop those models. And we also need the data to parameterize the established models to the systems that are of our interest. As Prousniet said, models come and go, but good data stay or are there forever. And that's true. Once something has been measured, it is the way it is. A colleague of mine phrased it slightly different. He said, be careful with experimental data. And what he meant is that even under well-conditioned environment, you can do a lot of experiments, but then still you have to understand what you're looking at. So that's why he said, be careful with experimental data. But he also said, be very careful with other data. So he puts everything in a perspective. Then if it comes to electrolytes, I want to refer to Mikko Mikkelsen, another great person in our community who we lost this year. And his famous saying was that life is too short to worry about electrolytes. And I got this quote from Georges Contra-Georges. Later he also mentioned that life has not got any longer. I agree with him, and that's also probably why we're here all together to discuss electrolytes. At the same time, from an industrial perspective, we're not allowed to say that life is too short. We have to deal with it, so we have to find ways to deal with it. And that brings us to the challenges of the models. If you look at the model, there are certain models which are frequently used by the industrial community. But why are these models so difficult? Because if you look at the number of models available for electrolytes, they're still limited, and they work in certain areas, but they don't work in others. So why is that? Well, probably I'm not the best person here in this audience to explain. You probably can do it much better yourself. But it's about the added complexity if you compare it to the non-electrolytes. If you have salts and they dissolve, they will dissociate, but to which degree? And what you can see is that models are very sensitive to this dissociation degree. Well, it has a direct effect on the molar fractions. Also, to describe the much stronger effects between the ions and its environment, it requires different kind of phenomena to be taken into account than what we are used to if it comes to non-electrolytes. Moreover, the data are rather restricted. There's data available for certain systems, but it's not very widespread, as we just discussed. And there's an ugly parameterization, excuse me to use this word, but now I jumped forward. But the parameterization of an electrolyte model is very challenging. So what do? I think we try to reach out to try to emphasize that we have this problem, and also to try to find solutions to resolve this problem. And here I just show you a few examples of recent developments, including the overview paper on industrial requirements that I hope will be transformed also into a position paper where we can explain to others the importance of thermodynamics and also the importance of electrolyte thermodynamics. Elitair, sponsor of this conference, is a joint industrial project by IFPN, where a number of industrial members are active and where we try to define the general rules and general approaches that are necessary. Very happy to see the ERCE grant given to Georgius, just as an example showing that governmental bodies do recognize the importance. And then a very old paper by me, almost 10 years old, actually even over 10 years old by now, where we did the first comparison of different activity coefficient models that are used by industry, being OLI, ALAC NRTL, and extended UniQuark. So now I want to shift to a few examples from Nouryon, where I just want to show some sort of common practice that we have been doing, actually related to the challenges that I described before. So if you look at the typical production process, it comprises a number of steps. In the midst, of course, is the reaction where the chemistry takes place. But before you do that, you need to do something, and afterwards you certainly need to do some separation. Part of the separation, of course, is also the waste treatment, which we try to minimize. And you will see recycles in those processes. And in these steps, electrolytes can basically be everywhere, not only in the process steps, also in the product streams themselves, of course. And I want to go through 4 examples, if time allows me, which are all separate processes related to the hydrochlorination of methanol, related to removal of HCl. By the way, those are related to the same process. A brine treatment, which is a different process, and production of NaSH, sodium hydrosulfide, which is also a different process. So to start with the chloromethane production, so that's related to the importance of electrolyte thermodynamics in the reaction and in the separation. The process comprises a number of steps. Actually, it's sort of two types of reactions combined. The first, you have hydrochlorination of methanol. Let me use the laser. So the first step, you do the hydrochlorination of methanol using HCl was actually formed in the second step. You form chloromethane and water. You need to do some separation, obviously. And then the chloromethane either is used as a product, or it can be sent to the second step where you do chlorination with real chlorine and methane, where you get a mixture of different levels of chlorinated methanes, and then of course that you need to separate. And HCl is produced as a byproduct in that step. So if you look at the separation, there are two clear parts where you do have a separation challenge. And if you look more closely, those systems comprise organics, water, and electrolytes. Well, this four-step process is a very much summarized overview of the plant. It comprises quite a number of unit operations. So to describe all of them and have a decent model, that takes a very long time. So we have decided to do a shortcut. So here the shortcut, here you get an impression of the kind of molecules present in the system. And actually, if you want to do a very decent job, you would need a mixed solvent electrolyte type of model. And here it should be noted that HCl is not the only electrolyte, but we wanted to have a universal model. And there we decided to use PSRK, for which we got parameterization through the UNIFAC consortium. And for more dedicated sizing and design, we used dedicated NRTL models for the separate unit operations. So here you see a TXY diagram for the system HCl and water. On the left-hand side, there is the NRTL, on the right-hand side, the PSRK. And you can see, even though PSRK fundamentally is not the right model, the representation is okay. And that's what we're after. We are after a decent representation of the problem. So that's what we applied in the first part of the studies to use PSRK, which we could develop much faster. We could get an impression of the recycle streams and everything. And then in a later stage, we started to zoom in and develop a more dedicated model. So the second example is also related to this process. It's related to the hydrochlorination of methanol, so the first reaction step. And if you look at the information, basically what you do is you have the reaction between HCl and methanol, and it gives you chloromethane and water. You have a byproduct, which is DME formation, so dimethyl ether, which is a reaction catalyzed by acidity. And if you have the ether can also react with HCl and form the chloromethane and methanol. In literature, in 2011, there is this information about the kinetics. And if you look at the kinetics more in depth, then you see that there's surprising high order of reaction for HCl. And also the DME formation seems odd. If you look at the stoichiometry of the DME, you would expect sort of second order, and you don't see much of an HCl effect, and certainly not a negative exponent. So what's happening here? So we decided to look into the mechanism, and if the mechanism, this is the hypothesis of the reaction mechanism, that the reaction goes through this protonated intermediate, where methanol gets a proton from hydronium ion, and the intermediate then is reacted by nucleophilic attack by the chloride, and you get the chloromethane. So this is the major reaction, and if we continue, then this intermediate can also react with another methanol molecule, then you get the dialkyl ether, and this intermediate, of course, can also react with the chloride, so you can get to chloromethane. So this is the hypothesis, and if we then realize that the acid-base reactions are fast, the nucleophilic effects are relatively slow, you could formulate a reaction scheme where you say that the methanol and this protonated activated form of it is in equilibrium with the hydronium ions and water involved, and that intermediate reacts with the chloride. And if you write that down, then you get to this kind of reaction equations, where you get this form in there, which represent basically the HCl, the hydrochloric acid concentration effect. So if we want to model it, then basically we would need a model that describes the effects of all the intermediates. But we started to look only at the water HCl, and that's for a very simple reason, because that is pretty well available. So then, you get to a typical PXI diagram of water and HCl at 100 degrees C. And from that, you can also see what are the activities of the respective species as a function of the concentration of HCl. And if you then put into the form that we're using in this equation, you get this kind of curve. And if you then take the fit as shown by the drawn curve, you see that this is sixth order. And that is exactly what is reported. So that gave us very good feeling about it. What's even more interesting, just looking at this subsystem only, that if you do the same calculation but at different temperature, you see that the order starts to change. So both we could explain the strange sixth order, but we also could explain the seeming dependency of the order of temperature. And that's basically what I said. So here the take-home message is that through a fundamental insight, we got very quickly access to a good understanding of the process. So we understood why the sixth order was there. We also understood that at different conditions, there will be different orders. And we could do that by looking just at the subsystem. Well, it will not come as a surprise that when we continued, we improved the models. Okay, the third example is about sodium hydrosulfide production. Sodium hydrosulfide, or NASH as we call it, can be produced in two ways: from sodium sulfide, as shown here by the reaction stoichiometry, or with reaction with caustic. And if you do the reaction with caustic, then in principle you first make the sulfide in situ, and then that is further converted into the NASH. There are some constraints, such as the solution should be homogeneous. Only small amounts of solids are allowed, and hence it's very useful to look into what is the solubility, where are my solubility constraints. So if you just look at the first process, it's the reaction of sulfide and H2S. then you can make a ternary diagram like this one shown here. It's a little bit of an artist impression, but I guess you get the picture. What's interesting to note that in this special case, in this ternary plot, also the positions or the relative position of caustic and H2S are also defined. If you look at the stoichiometry of conversion, then you can say that the relative position of H2S is given by this equation, and similarly the relative position of caustic. So these points are fixed in this graph. So you can make use of this, what we call extended ternary diagram, by plotting the subsequent ternaries to it. And then you get this overview, which you then can color in for management if you wish, where you can see that this is the liquidus zone. This is the region where you have a single solid in coexisting with a liquid. Here you have this situation, the envelope, where you have two solids and a liquid, the same here, and here you have solids only. And here you also have gas because there's HCS, so we didn't fill that in. The interesting thing is, if you plot it like this, you can see that if you plot the work line for the operation with caustic and H2S, it really goes through according to this line. And you can see that you would like to avoid this green region. You want to be here where my laser is, roughly. So the visualization is very strong. The problem, of course, is that we as thermodynamicists, we are used to the ternary diagrams, but other people have a tendency to be afraid of it. So it needs some explanation and sometimes a little bit of guidance to people less familiar to it. But if you explain that it is just a visualization tool, but very powerful, then people grab the idea. I didn't mention, or I did not explicitly tell it, but actually, if you look at the curve, this curve is the solubility for the sulfide. There is not much information for the hydrosulfide, so we will be interested to know more about that system. So if anybody could help us here, we would be very happy. In view of time, I will skip this example and move on to the end, my perspective. I hope that through this presentation, I've been able to explain to you that the various elements are crucial and that we need all of them. And I would like to emphasize here that data are very crucial. Sometimes it looks like it's the forgotten, the forgotten element, because data are very crucial. Data is the beginning of everything. But of course, fundamental understanding is also key. And in the end, for industrial applications, we should realize that we can live with models which maybe not be perfect, but as long as they are representative. But of course, our life gets much more easy if the models are completely right. We would like to have pragmatic approaches. So parameterization of the current models is a bit of a challenge. And if it comes to parameterization, there are two aspects to it. That is simple data measurements. So could we maybe define simple ways of measurements that provide us data that we can use for the models? And the other aspect is that we have appropriate regression methods, because regression also remains a problem. Maybe also relate to the fact that the parameterization, the parameters are sometimes highly linked. Sort of an holy grail. Quick prediction methods would be appreciated. What we do typically is looking at systems which are similar to ours, so the benchmarking approach. But if there are other ways to doing this kind of things, those will be of huge value. Not mentioned at all in this presentation, but that's the uncertainty. I think for all models in chemical engineering, we are typically very happy if, and certainly if it's a huge flow sheet, if it gets to a convergence. But actually, we also would like to know how certain are we about the outcome of our calculation results. Electrolytes are everywhere, and I think we know that as our community, but it would be good if we can raise the awareness to the general public, and hence through that to policymakers and decision makers, and not only thinking about the governmental bodies, but also people at the universities and at the companies. Then, yeah, this brings me to the end of this presentation. I just want to mention to you that tomorrow we're going to have the IUT on electrothermodynamic challenges, where we focus indeed on the challenges that we have in industry. We would like to have an intimate discussion with everyone present, how we can move that to the next level. And this is done by three major questions through which we want to have our discussion. So this brings me to the end. Let's grow the forest together. Thank you very much for your attention.
Thank you very much, Antoon, for your very nice and very clear talk. And I think there are quite a lot of questions. So please, if you have a question, raise your hand. So maybe yeah, there is one in the back. Please ask, just ask. So maybe I start with the first question, Antoon. So you have shown a very impressive combination of phase equilibria, that means activity coefficients, and also reaction equilibria. So it was very nice. So thank you very much. My question is, the parameters for the electrolytes you have shown that you work in aqueous systems and also organic solvents, for example, in methanol. So do you use the same parameters, whatever the solvent is?
Thank you for your question. What we try, well, in this case, we use ALAC NRTL, and the major reason is that we use Aspen Plus typically as for our flow sheeting. So we have to use the models which are available in the software package. Since we're using ALAC NRTL, typically we build up the system from binary, or if it comes to electrolyte ternary kind of information. So also with methanol, yeah, we looked at the data available for instance, hydrochloric acid and methanol under non-reactive conditions and try to parameterize that part of the model. But that's not an easy task, I can tell you.
Yeah, certainly the case. So the parameters are for electrolytes or for ions?
Yeah, I'm not sure if I understand your question. It's the way that Aspen is set up, you're always talking about ion pairs and the interaction of ion pairs and another molecule.
So for example, if I have a sodium ion, so it has different parameters depending on whether it's sodium chloride or sodium sulfate, for example.
Yeah, absolutely. That's the way it's set up. So there is a distinction made between, yeah, it's counter ion.
Okay, so thank you. Are there any other questions? So yeah, please just ask. I cannot see who is asking, but there is somebody. Just ask, please.
Yes, hello. Is this working?
Yes, it is.
Okay, perfect, nice. Antoon, thanks for your talk. It was really clear actually. I only had like at one point I was a bit confused when you started talking about this reactivity rate. where you basically said like that it was an interesting part where you started to explain basically why this was then to the power of 6. So you showed all these schemes and how then these reactions were taking place and intermediate steps. Then in the end, actually, if I understood correctly, then you showed basically that this experimental data and I believe now it was basically the 6 came from an empirical fit. And in the end, like that you saw like from experimental data on that at 25 degrees it was a 6 or at 50 degrees Celsius. And when you lower it to 25, then it was to the power of 4. And at 100 degrees Celsius, it was to the power of 8. Was there a physics-based explanation behind this, or was this then purely statistics-based?
Thanks for your question. Actually, this came forward from the model. I have to scroll back. It takes a little bit of time. Here, I think exactly. You're referring to this curve. Actually, all these points are calculated points from the NRTL model for hydrochloric acid. And if you take from that model, what are the activities at given concentration of HCl? I see that I'm using my pointer, but not the laser, so maybe that's better. So if you look at the concentration of HCl, then you have a certain ratio of water activity and chloride activity and water activity. And if you take this quotient, that is basically what is here on the left, you get these points. And then through these points, except for the very low concentrations, you can do a fit, and then you get this 6th order fit. Now if you do that for a different temperature, so for instance here 200 C, you get a different order. Well, obviously we also did experiments, and that was confirmed in those experiments. But I've not shown those results. Here, what I wanted to show is that even if you talk about a subject which seems further away from thermodynamics, namely reaction kinetics, still your fundamental understanding in thermodynamics can help you to understand your reaction rates. And that has to do with the fact that the first step in this whole process is governed by gamma equilibrium. Clarify.
No, definitely. I thought the 6 was basically the input for your model, but the activities were calculated, and then the model basically showed you then this is has to be to the power of 6, or and this was then also confirmed by the experiments. Yes.
Yeah, that's correct.
Clear.
Okay, perfect. Thank you. Christoph, there's another question from you.
Yeah. Thanks so much, Anton. This is Christoph. Can you hear me?
Yes, I can. Thank you.
Okay, great. So thanks a lot for your talk. Very, very interesting. And I had exactly also a question to this slide. So I think we all agree that it's so important to express also the kinetics by accounting for the thermodynamic activities in the kinetics. So this is really important. And my question is, on the course of the reaction, there is like methanol production, or at least there's a consumption of methanol, either the way you put it. So is the term that you are showing here, is that depending also on the methanol content?
Thanks for your question. What I'm showing here, this relation between this what we call the hydrochlorination activity and the HCl concentration is only true for an aqueous system. So if no other material is present, in that sense, the presence of methanol will affect that. But it didn't have a huge effect. I should emphasize again that when we started this project, we were surprised by this finding from literature that this was 6th order, because typically 6th order, it cannot be the intrinsic reaction, if you understand what I mean. Intrinsic reactions typically 2 molecules that react together. So order of 2 is more logical, for instance. So 6th order is very huge, and through this understanding, before actually we did any experiments, we were able to already understand why this 6th order came from. And if it comes to the methanol, yeah, methanol here again, methanol is described as an activity. So also the concentration effect of methanol is depending on its environment. But it's not such a strong function as you see here for the HCl concentration, if you wish. Does this answer your question?
Yes, thank you very much.
So we have time for another short question. Is there any? Yeah, there is one. I cannot see your name, but please just ask.
Hello, can everyone hear me? It's William Smith.
I can hear you.
Yes, thank you very much for your very interesting talk. I noticed that from an overarching point of view, the methodology seems to be based on these simulation packages like ASPE Plus you're mentioning. Now, the data that goes into that certainly takes a lot of experimental work to get the parameters and to fit the models and so on. Now, as someone who works in the area of molecular simulation, we can predict these things. Now, what do you see in the future for this kind of work?
Thanks for this question, and it's a very good question. And I guess it relates to the general perception that data are very crucial, and data are experimental data. I want to emphasize that because I personally feel that it's undervalued by many. But the molecular simulations, if you wish, are of course also a very fruitful source for data. And the status that it is at, or at least in my conception, is that it's particularly valuable if you have systems which are very difficult to measure because of toxicity, for instance, or because of reactivity. You can basically do calculations while putting off the reaction, which is difficult in reality. I'm not sure whether we are already at that level that we can sort of exchange really the experiments by in situ or in silico calculations. But this is a bit of my personal opinion.
Okay, thank you very much for your viewpoint.
So thank you very much, Antoon, again, also for the discussion. Let's try to give the speaker an applause by pressing F4. You can try this.